Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss another one topic regarding the operating characteristics curves, or which is also known as constant speed curves. In our last lecture, we have seen the main characteristics curves. In that, we have discussed many things. Here, we'll see in the operating characteristics curves, we'll discuss about the relation between like efficiency and power versus discharge. So these curves actually, if you see this diagram I have taken from the book. So this diagram actually it shows the relation between the power and with respect to discharge and efficiency with respect to discharge. So this operating characteristics curves actually it shows the performance. It shows the performance of the turbine. So performance in the sense we can write like what we used to call the performance of a turbine. So there we need to see what is the power of the turbine and what is the efficiency. The efficiency also we need to consider the overall efficiency. This performance of the turbine we need to compare, like we need to see with respect to we can say or versus discharge, and here we need to consider that speed is constant. The speed is constant here, and we know that a turbine will run at a constant head. So head also here constant, because we cannot change the head multiple times for a turbine. It is fixed. Okay, so these two parameters of this we need to see with respect to the discharge. Okay, so here in the x-axis we have taken the parameter of discharge, and in the y-axis we have taken this efficiency and power. Okay, and we can, as I told you, that we need to see with respect to speed constant. That's why it is called constant speed curves. Okay, now in the constant speed curves actually this also will help the engineers to understand the behavior of the turbine. Okay, this constant speed curves will be help the engineers to understand the behavior of the turbine at different loads. Okay, what is the performance or what is the behavior of the turbine at different load conditions, and different operating conditions will be there. And this test actually it's shows like as constant speed with respect to, like as I told you, head and speed need to be taken constant, and the relation between this discharge and efficiency need to be compared. Actually, in our previous lecture already I told you that we have total 6 number of parameters are there. Operating parameters are there, total 6 are there. What are the 6 are? Now we know that one is head, one is speed, one is discharge, another one is power, another one is efficiency, overall efficiency, and another one is that gate opening. So these are the 6 parameters are there to find out the performance of the turbine. So out of these 6 parameters, we have 3 parameters, independent parameters are there. That is N and H and Q. So these 3 are actually, it is called independent parameters. So now if you see here, N and H already it is constant here. Okay. So the next one is what? The discharge. So discharge need to compare. So the discharge need to compare with respect to this power and efficiency. That's what it is done here. So in this, let's try to understand how this curves, like how this performance happened here. Okay, so first one, let's see this curve is actually for power. Okay, this curve is actually for power one. So power versus this power versus discharge. So in the power versus discharge, okay, we can see here that as the discharge increases, the power also increases. So this relation actually, like here if you see, our discharge increased, power also increased. Okay, so this one we can take a relation like correlation is there. If I tell that power is directly proportional to Q, discharge, and also I can say that it also directly proportional to head also, but here I'll tell the head is constant here. So the head constant, P is directly proportional to Q. So that means when discharge is more, when the discharge is more, that means more water strikes the vanes, or more water strikes the runner blades. Okay, so discharge more means we can say the water strikes the runner blade, okay, higher, and once it is striking this at higher velocity, we can say, or at more water strikes the blade or this runner, then we can say that there is a momentum transfer. Okay, there is more momentum transfer uh, happened there, or we can say the momentum increased here. Okay, the momentum transfer increases. So once momentum increased, then we can say that the power and torque. Okay, here we need to consider torque and power. So both will be increased here, because once discharge increased, that discharge increased in the sense it's like, you know, it's striking this blade with the high one. Okay, so finally, like, see, discharge at the last it will be come out, but thing is that when how much water will be supplied to that runner, so based on that the discharge will be more. So once we'll supply the water at the more at the inlet condition, then we'll get more discharge at outlet condition. So similarly, when water is supplied more, that means water strikes the blade at high, so there more momentum transfer happens. Okay, and now you can see at the starting, if you see the curves, like both it started increasing. Okay, both like efficiency I'll tell you later. First we can see this one, power. So efficiency also similar kind, like at initial conditions, if you see this efficiency is increased with respect to discharge and like with respect to discharge, we can say. So power will be continuously increasing more, because how much discharge will be, how much discharge will give, that much power will be generated here. And after a optimum one, it started fall down actually. So that's why it is given here. This breaking point is given here. That means maximum we can go up to a limit. But in the efficiency, if you see, okay, in the efficiency, if you see, it falls after a certain point, maximum reaching point. After that, it started falling. That means at this point, what I can say that efficiency, when it is reached at the maximum point, at the high discharge, okay, at the high discharge, if I consider, so at that point, what can be expected, like the flow separation started occurring there. So we can say the flow separation occurs. The flow separation occurs at the high speed or a high discharge, we can say. That means flow separation, why it occurs, because more turbulence will be there. So turbulence also increases here at this point. Turbulence also here, flow separation occurs, increases, and we can turbulence also it increases at this point at the high discharge, and that's why we can say there is some losses increases. Okay, there is some losses increased at this point. What kind of losses? Either it may be a mechanical loss or it may be a hydraulic loss. So the losses may be increased at that point. So due to this region, so up to a maximum point, we can say that the efficiency will be increased, and after that it started falling down. So efficiency will be increased up to a certain point, up to a certain point, and after that it started falls. That means decreasing. How much discharge if increase, it won't give any kind of output to the efficiency terminology. Similar in the case of power also, it will reach up to this, and after that it started maybe falling here. Okay, due to this kind of regions also may be taken for that also. Now one more thing we can see, that at the starting of this, there is no curves are there, like these curves are not started from the origin point. Why? Because so this region actually, we can say like a certain amount of discharge required, or certain amount of water is required, okay, to produce the power. Because initially if you give water immediately, and it does not mean that immediately it will give some power and efficiency. So initially, if you see, initially we need to supply, initially water need to supply, okay, or you can say the water in the sense the quantity of water, that means nothing but that discharge of that water is required to produce power, to produce power. So why? Because this discharge is required, or why this water is required initially to create power. Initial conditions, it need to overcome the friction. That's why it is given the discharge for overcoming the friction. Okay, so initially we need to overcome the friction in that, So for that we need some kind of some amount of water in that. Again, I can say, so turbine actually it cannot produce power immediately. It's zero discharge. Okay, this is the 0 point, origin point in the sense 0 point. So zero discharge, there is no chance of like power development. So we can say that is one more reason. And the efficiency also same thing. The zero discharge, how it will be started. So slowly it need to give some gap that the performance will be started after some point from the origin point. Okay, and at this point also the efficiency will be very less. If you consider also very less, negligible will be there. That's why it is ignored. And because no water flow, zero in the sense no water flow, so no momentum created. So no momentum in that means no power generated here. So initially, again one more point also in that I'll tell you that some kind of losses are there. Some kind of that losses, as I told you, that mechanical loss or maybe hydraulic loss is there. To overcome that loss, you can say friction, as I told you, that friction, overcome that friction, and some minimum flow is required to overcome that. That's why it's given some gap here. So I hope you understand this theory, how it is working for a turbine. So this operating condition, operating characteristic curves, or it is called as a constant speed curves for turbine. So this will be give a much more information about the behavior and performance of the turbine to an engineer. I hope you understand this lecture. If you are having any kind of doubt and query, you can give a comment on the comment box. Thank you all.